Let's remember that our main purpose in doing predictive AI is to make predictions for data whose true result we don't know yet, but we're training the model up with data that we know the results for, and the model has been steered or trained to do well on that. We'd like to see how well it does on some data that it hasn't seen before. It's a lot like the way we do exams in classes. We don't give students a list of the exact questions and answers that will be on the exam, usually, because the students might just memorize the questions and answers without attempting to understand the concepts. So then how do we take that and apply it to machine learning or AI? Let's look at an Excel sheet that has data from the US Census. So how many people are in the country every 10 years, and we'll fit some trend lines to it. So the first census was in 1790. The population that it recorded was 3.9 million, for example. Um, with any data set, we should ask who is included or left out of this data set, whether on purpose or by neglect or accident. Um, so in theory, the population should be a complete count of people in the US. How good of a job did they do with Native American people? I would guess not a very good job. In fact, it wasn't until the 1940s or so that a law clarified that Native American people qualified for citizenship. Um, and there's questions about should this count citizens or not. There was a major issue with the U.S. Civil War, you might remember, around 1850, 1860, where 1870, where Black people were counted as less than a full person. How did that impact? That's called the Three-Fifths Compromise. How did that impact these numbers? I don't know exactly. But again, with any data set, you should be asking questions about like, what's the definition of a person here? Um, so looking at the growth of the curve here, I've fitted a polynomial trend line because it kind of looks like part of a parabola, right? And seems like it's doing a good job. There's this thing called R squared that measures kind of how well the data that you have matches the trend line. And R squared values near one are usually better. But it's not like the only way we judge it, but it is one of the important ways we judge it. R squared is always between 0 and 1. So this is for a parabola. You can see the x squared here. I've also over here fit a cubic. You can see x cubed plus something or other, x squared, etc. And how do these two curves compare to each other? Well, by eye, I'd say they look pretty similar. Um, look at the r squareds. The r squared for the cubic is slightly higher than the r squared for the parabola. So does that mean that a cubic is a better model for the US population growth than the parabola is? So we should think about that. Um, also, math on large numbers and polynomials, it often goes better when you make the numbers more reasonable. So it's fairly common to do something like years since 1900, and some of them can be negative if they were before 1900. So that's just what's going on there. Um, it's interesting to note that when we included a cubic term, the coefficient on the x squared did not stay exactly the same. It's pretty similar, but actually, if I showed more digits, we could see that it's different. The coefficient on the x is a little different. The intercept coefficient, the intercept is slightly different. So there's no guarantee that the weights you have on things will stay the same if you include new flexibility, like including a new cubic term. So this model is doing a better job predicting the data in the data set. But what if we wanted to use it to predict future data, like like the 2030 census, the 2040 census? Well, we could make predictions now and then wait until 2030 or 2040 rolls around, but then we'd be waiting a long time. Another way we can do it is pretend that we don't know what the most recent results were. Like pretend it's like we only have data from up to 1970, for example. Fit our models to that, then make predictions for what is the future from the perspective of 1970, and then reveal what our hidden data was that the model wasn't trained on, and see which model did better. So let's come do that here. So we've got our training data up to 1960. We fit our parabola and our cubic model based on that. So up to the blue dot here. And then we use those to make predictions into what is the future from 1970's point of view. Um, and then compare those to what the actual data was that we kind of held back. And the cubic is the red dotted trend line, and the parabola is the black solid trend line. So we can see that the parabola is actually doing a better job predicting the future based on its training than the cubic did, even though the cubic had a higher R squared. So what we've done is we've broken the data into two parts called the training part of the data and the test part of the data. We train our models on the training data, make predictions for the test data, and then compare those predictions to the actual results of the test data. Um, uh, that's what we just said. Um, so uh, a typical split would be like 80% of your data for training and the other 20% for testing. Um, and then we tend to prefer the model that does better predicting on the test set. If the data is in time order, like the census data we just looked at, we often split it with the early data being training and the later being test, like we just saw. If there's no time order, then we might just choose 80% of the rows of the data randomly to be in the training set and the other 20% in the test set. Um, if there are subgroups of interest by race, gender, veteran status, for example, it's often good to split each group 80-20, so each group is roughly equally represented in the training and the test. That's called stratified sampling. It's often a good idea. It's often essential. So got to keep that in mind. If we're worried about how the 80-20 split might affect the results, if we're just choosing randomly, what we can do is split the data into 5 sets, each 20%, or each random or stratified at least. We could call those 5 sets A, B, C, D, E. Then we would like put A, B, C, and D together into one lump. That would be 80%. Train on that, and then train our two models on that, and then predict from those models for set E, and then evaluate the prediction accuracy. Then train on A, B, C, and E, skipping D, and test on D. So basically each set of 20% gets a chance to be the test set. So that's called five-fold cross-validation. It is 5 times as much work as just doing the split once, but is more reliable. You can also do 10-fold or 15-fold or whatever you have time for. So that is the idea of train test split and cross-validation, which is a pretty important, fairly standard procedure in a lot of predictive AI.